Hi, and welcome to a live demonstration of our system to find the direction of arrival within a sector of interest. DOA estimation is widely used in 5G and many other sensing systems. The goal here is to determine the direction of incoming signals that can come from a source or from a target. Let's now dive into our system, which is based on ultrasound waves. We built a uniform linear array of n microphones that can each receive 40 kHz ultrasound signals. These are sound waves that you and I can't really hear, but we could do great things with these inaudible waves. To estimate the direction of arrival of the transmitted signal, we start with sector search, which is a basic procedure that's also used in 5G systems. In sector search, the receiver scans distinct non overlapping sectors. For example, let's say we point the array towards sector 1 and measure the received power. Now, if this received power is low, which is the case in this example, the source likely isn't there in sector 1. Then we scan sector 2, where we observe a higher received power in this example. Finally, scanning sector 3 yields lower power again, and at this stage you can conclude that the source is in sector 2. Once we've identified the sector, our goal next is to find the exact direction of arrival within that sector. And we've got a challenge here. The challenge is that we have access to a limited number of microphone measurements similar to a sparse array. This challenge arises in low power receivers where the number of analog to digital converters ADCs is smaller than the number of microphones N. Such receivers have been discussed in the context of 5G and they are called switched receiver arrays. So because you have switches here, the receiver can only select M of the N possible microphones. The question that we have now is what is the subset of microphones that is best for direction estimation within that sector? Let's take a look at one such subset. Turning on just few microphone elements means that we subsample a spatial signal. And this results in aliases, which are basically copies of the target in the angle domain. When these aliases are high in the sector of interest, it's bad because you end up with false alarms and even misdetections. Let's look at a different configuration now. Here, the aliases inside the sector are lower, which is exactly what we want. I should also mention here that compared to the last profile, the aliases here are higher outside the sector. And that's alright as we only care about the identified sector. Now, to formally arrive at a good microphone subset, I'm going to develop an optimization problem. This problem finds a binary switch configuration S that minimizes the peak aliasing artifacts within the sector of interest. The constraint here is that the sum of entries in S should be M, which is the number of ADCs in our system. We solve this problem using an integer program method for M equals 4, and this is our solution. And now for the most exciting part, our live demonstration. In this section, I'm going to show two things. First, how does our system identify the best sector? And second, how do we obtain a fine DOA estimate with the optimized subset we saw in the last slide? So let's dive in and see our demo in action. Alright, so here is our 40 kHz ultrasound transmitter. And now let's move on to the receiver that has 8 microphone elements. Let's take a look at sector sweep with 3 sector searches. And now the receiver figured out the right sector and let's look at DOA estimation with our approach. As you can see from this plot, our method can correctly identify the direction of arrival as 0.1 degrees. Now you do see aliases which are at about 60 degrees and negative 60 degrees, and they don't really matter because we already know that the sector of interest is between minus 25 and 25. So this concludes our live demonstration, and thank you for listening.